Beneath the streets of Los Angeles, San Bernardino, Riverside, and the Coachella Valley, geologists have confirmed a development they have been tracking quietly for years. Two of Southern California's most important fault systems are now carrying more built-up stress than at any point in the past 1,000 years of their modeled history. Scientists describe this condition as critically loaded. And at the location where those two faults come together, researchers have identified a junction with an unsettling nickname, the Earthquake Gate. A major new study has examined what this could mean for one of the most densely populated regions in the United States. The findings do not predict that a major earthquake is about to happen, and they do not provide a date for the next rupture. But they do show that the stress conditions across two neighboring fault systems are unusually well aligned, creating the possibility that a future rupture could travel farther and cause more damage than an earthquake limited to only one fault. The two systems at the center of the research are the Southern San Andreas Fault and the San Jacinto Fault. They run roughly parallel through Southern California, and both are capable of producing powerful earthquakes independently. For decades, seismologists studied them mainly as separate systems, tracking the individual earthquake histories and stress levels of each fault. The new research takes a different approach by focusing on how the two faults interact, influence one another, and transfer stress over long periods of time. The study, published in the Journal of Geophysical Research and led by geologist Lillian Burkhardt at the University of Hawaii at Manoa, used detailed computer simulations to reconstruct approximately 1,000 years of major earthquake activity across the region. By combining geological evidence, known fault properties, and established models of stress transfer, the research team attempted to estimate how strain has accumulated and shifted between these neighboring fault segments over centuries. The results were significant. In the researchers' modeled history, the stress levels on both the Southern San Andreas and San Jacinto faults have now reached their highest point. Just as important, both systems are carrying remarkably similar levels of stored pressure. That similarity is central to the study's conclusions. When two neighboring faults contain very different amounts of stress, a rupture on one may be less likely to trigger a large rupture on the other. But when their stress levels are closely matched, the two systems can influence each other more effectively. A rupture that begins on one fault may be capable of crossing into the other, depending on the exact conditions at the moment the earthquake begins. The critical location is Cajon Pass, a mountain junction northeast of Los Angeles near San Bernardino. This is where the San Andreas and San Jacinto fault systems converge. Burkhardt's research team refers to the junction as an earthquake gate because it may help determine whether a rupture remains confined to one fault or crosses over and develops into a much larger event involving both systems. The gate is not a literal barrier. It is a physical and geological transition zone where the behavior of one fault can affect the other. According to the study, one of the factors that determines whether the gate stays closed or effectively opens is how closely the stress levels on the two faults are aligned. Right now, the models indicate that both systems are loaded to nearly the same critical level, which is the condition the researchers identify as making a multi-fault rupture more plausible than it would be if the two faults carried very different amounts of stress. That possibility matters because the size of an earthquake is strongly influenced by how much of a fault ruptures. An event limited to one segment is still capable of causing severe damage, but its reach remains constrained by the length and structure of that fault. A rupture that crosses Cajon Pass and continues across both the San Andreas and San Jacinto systems could become considerably longer and more powerful. Such an event could affect Los Angeles, San Bernardino, Riverside, and the Coachella Valley, all areas containing large populations, major transportation networks, dense development, and critical infrastructure. The difference between a single fault rupture and a connected rupture across both systems could therefore be substantial. To understand why the current findings matter, however, it is important to place them within Southern California's much longer earthquake history. Southern California's last comparably major earthquake did not occur on the specific southern fault sections examined in this new study. Instead, one of the most famous earthquakes in American history struck much farther north. On April 18, 1906, a magnitude 7.9 earthquake ruptured the northern San Andreas Fault near San Francisco, killing approximately 3,000 people and devastating large parts of the Bay Area. That earthquake released a tremendous amount of accumulated stress along the section that ruptured, but it did not erase the pressure building along the southern San Andreas or the neighboring San Jacinto Fault. Earthquakes generally release stress only across the portions of the fault system that actually rupture. A major event in one part of a fault network does not automatically relieve strain accumulating hundreds of miles away. That means the southern segments examined in the new research continued building stress independently after the 1906 earthquake. In some locations, strain has continued accumulating for centuries. The quiet behavior of a fault should not be mistaken for a lack of activity beneath the surface. It can mean that movement is occurring gradually and silently, or that stress is being stored rather than released through a large rupture. Outside experts have described the new research as a useful contribution to earthquake science rather than simply another warning about an inevitable disaster. Bill McGuire, Professor Emeritus of Geophysical and Climate Hazards at University College London, was not directly involved in the study, but he described the earthquake gate concept as a valuable and elegant scientific idea. He also highlighted the finding that stress levels on the two faults have reached an unusually high point as important for understanding future risk around the Los Angeles region. McGuire noted that large earthquakes are considered overdue in both Northern California, including the San Francisco Bay Area, and Southern California, including the greater Los Angeles region. That assessment reflects a broader scientific understanding of long-term seismic risk, not a prediction produced by this single study. This distinction is essential. The research does not say that a major earthquake will strike tomorrow, next month, or within a specific number of years. It does not identify an exact date, and it does not claim that a rupture is inevitable. What it shows is that the current stress conditions across these two faults are unusually high within the 1,000-year period represented by the model. That raises the calculated probability of a significant earthquake, but it does not turn that probability into a precise forecast. Earthquake science still cannot predict the exact timing of a major rupture with meaningful accuracy. Even advanced computer simulations cannot determine the specific day when stored stress will overcome friction along a fault. What researchers can do is improve the understanding of relative risk. They can identify which fault systems appear to be carrying the greatest accumulated strain, which areas may be capable of interacting, and where emergency planners should focus preparedness efforts. That measured conclusion is important because some coverage of complex scientific studies can become more dramatic than the original research supports. Credible science reporting has generally described this study as a significant update to long-term earthquake risk assessments while still explaining its limitations. Less careful commentary may turn the findings into an imminent danger narrative, even though the published research does not make that claim. Anyone trying to understand the story should look for direct references to the peer-reviewed study rather than relying on secondhand descriptions. The key message is not that scientists know when the next earthquake will happen. The message is that two major faults are currently modeled as being unusually stressed and unusually well-aligned, which may affect the way a future earthquake develops. There is also important context that prevents this research from becoming a story of helplessness. Southern California is far better prepared today than it was during the 1906 San Francisco earthquake. Modern building codes have been developed and repeatedly updated to help structures withstand strong shaking. Engineers understand seismic forces more clearly, emergency agencies have detailed response plans, and warning systems can provide limited notice once an earthquake has already begun. None of that eliminates the danger. A large rupture involving both fault systems could still produce serious, potentially catastrophic damage. But modern construction standards and preparedness measures can reduce loss of life and improve the ability of communities to recover. To understand how researchers reach their conclusions, it is necessary to examine the modeling process itself. Direct earthquake records in Southern California cover only a few hundred years at most. That is far too short to capture the full range of major events these faults are capable of producing. Human records may document some destructive earthquakes, but they cannot reveal the complete pattern of ruptures that occurred before written observations began. To overcome that limitation, researchers built computer simulations incorporating several types of information. They used the known physical properties of individual fault segments, geological evidence showing where earlier earthquakes disturbed rock layers, historical earthquake patterns, and established models describing how stress builds and transfers after a rupture. The researchers then ran those simulations across a modeled period of approximately 1,000 years. This created a longer statistical picture of how the southern San Andreas and San Jacinto fault systems may have behaved and interacted over time. Instead of comparing current conditions only with the limited number of earthquakes directly recorded in modern history, the team could compare them with a much broader modeled sequence. That approach allowed the researchers to identify the present conditions as an unusually extreme point within the modeled period. In other words, today's stress levels do not merely appear high compared with the last few decades. They stand out when compared with the larger 1,000-year reconstruction produced by the model. Computer simulations are not perfect replicas of nature. They depend on the quality of the geological data, the assumptions built into the equations, and the way researchers represent complicated fault behavior. But they allow scientists to examine time spans that cannot be studied through direct observation alone. Used carefully, such models can reveal patterns that would otherwise remain invisible. The geography of Cajon Pass is also central to the study. Located northeast of Los Angeles near San Bernardino, Cajon Pass lies where the San Bernardino Mountains meet the San Gabriel Mountains. The natural gap has long served as an important transportation corridor through difficult terrain. Major highways and rail lines pass through the area, connecting Southern California's inland communities with the greater Los Angeles region. Beneath that surface geography, the San Andreas and San Jacinto faults converge near the location. Cajon Pass is therefore important for two reasons at once. It is a crucial part of the region's transportation network, and it is a potential junction where two major fault systems may interact during a future earthquake. That overlap creates serious practical concerns. A major earthquake affecting Cajon Pass could damage highways, rail lines, bridges, power infrastructure, communication networks, and other systems that connect communities throughout Southern California. The broader area also contains critical facilities that would need to remain operational during a disaster. When an earthquake affects a location that serves as a transportation and infrastructure hub, the consequences can spread far beyond the immediate zone of shaking. Emergency planners must consider not only collapsed structures, but also blocked roads, damaged railways, disrupted electricity, broken water lines, fuel shortages, and communication failures. These effects can reinforce one another. A transportation shutdown can slow rescue operations. Power failures can affect hospitals and water systems. Damaged communication networks can make it harder for authorities to coordinate evacuations or deliver accurate information. That is why planning for this scenario is more complex than planning for an earthquake in an isolated region. A rupture at a critical junction could create a cascading, multi-system emergency. The earthquake itself might last only seconds or minutes, but the disruptions could continue for weeks or months depending on the damage. Seismologists studying Southern California have generally welcomed the new modeling approach because it focuses on interactions between neighboring faults. For much of the 20th century, earthquake research often examined individual fault segments separately. Scientists calculated risk based primarily on each fault's own history and expected behavior. Over the past several decades, improved computing power and more sophisticated geological data have changed that approach. Researchers increasingly recognize that faults do not always behave as independent systems. A rupture can alter stress on nearby segments, and the response of one fault can influence the conditions on another. The total risk in a region may therefore be greater, or sometimes different, than the simple combination of separate fault assessments. Burkhard's research contributes to that wider shift by modeling how two major fault systems influence each other over a long historical period. The California findings are important, but the methodology may prove just as valuable. If the approach remains reliable when tested against additional data, scientists could apply it to other regions where several major faults exist close together. Those regions include parts of Japan, Turkey, and other earthquake-prone areas where interconnected fault networks make risk assessment especially difficult. Before considering those broader applications, however, it is important to understand the individual history and significance of the two California faults involved. The San Andreas Fault stretches roughly 800 miles through California. It marks the boundary between the Pacific Plate and the North American Plate, which slide horizontally past one another. Geologists classify this as a transform boundary, different from the subduction zone dynamics found in places such as the Cascadia region of the Pacific Northwest. The San Andreas has produced some of the most significant earthquakes in recorded American history. The 1906 San Francisco earthquake ruptured its northern section. In 1857, a magnitude estimated at approximately 7.9 struck the central section in what is known as the Fort Tejon earthquake. These events released enormous amounts of stress along the portions of the fault that ruptured. The southern San Andreas segment, examined in the new study, has not experienced a comparably large rupture in a much longer period. That is one reason researchers regard it as carrying substantial, long-accumulated stress. Unlike the northern and central sections, which have each experienced major earthquakes within the past 2 centuries, parts of the southern system have remained comparatively quiet. Again, quiet does not mean safe. A fault may remain locked while the plates on either side continue trying to move. The motion is then converted into strain stored in the surrounding rock. Over time, that strain can increase until friction is overcome and the fault slips suddenly. The San Jacinto Fault is also significant, even though it receives less public attention than the more famous San Andreas. It runs largely parallel to the southern San Andreas through another densely populated part of Southern California. The San Jacinto system has produced several moderate and significant earthquakes of its own, and it is capable of generating damaging seismic events independently. Because the two fault systems run so close to each other, it is not enough to study them in isolation. Researchers need to know how stress accumulates on each fault, how a rupture on one could affect the other, and whether particular geological junctions make a connected rupture more likely. That is precisely the problem the new study attempts to address. A multi-fault earthquake would not automatically rupture every segment of both systems. The path would depend on the precise geometry of the faults, the direction of rupture, the depth and distribution of stored stress, and the frictional properties of the rocks involved. But when the stress levels on neighboring systems are closely matched, the conditions may be more favorable for a rupture to cross from one to the other. That possibility is what makes the earthquake gate concept useful, It gives scientists a way to discuss a specific location where the behavior of two major systems may be linked. The gate does not determine the future by itself, but it may influence whether an earthquake remains local to one fault or becomes part of a longer rupture. The broader evolution of earthquake science helps explain why this approach is gaining attention. For decades, scientists often evaluated each fault according to its own recurrence interval, geological record, and known rupture length. Those calculations remain valuable, but they can miss interactions that occur between adjacent faults. Modern modeling allows researchers to simulate many possible sequences rather than relying on a single historical pattern. A model can examine what happens when one fault ruptures, how that changes stress on nearby segments, and how those changes accumulate over decades or centuries. It can also test whether the current configuration resembles conditions that previously preceded connected ruptures within the modeled history. That does not turn the simulation into a crystal ball. Instead, it improves the map of possible outcomes. Earthquake risk is not a single number or a fixed prediction. It is a range of probabilities shaped by geology, time, fault interactions, and the limitations of available information. Researchers will likely continue refining the Southern California models as new observations become available. GPS stations are already tracking gradual ground deformation across the region, providing information about how the crust is moving. Seismologists also study smaller and more frequent earthquakes, which can reveal how stress is shifting across different fault segments. Every additional year of GPS and seismic monitoring adds another layer of information. Over time, those observations can help scientists test whether the model's assumptions match what is happening beneath the surface. The goal is not to predict the exact date of a future earthquake, but to improve confidence in the risk estimates and identify the areas where preparation can make the greatest difference. For residents, the practical message remains consistent with guidance that emergency planners and seismologists have issued for years. Have a clear emergency plan. Know how family members will communicate if phone networks fail. Secure heavy furniture and objects that could fall during shaking. Store essential supplies, and understand what to do when the earthquake begins. The new study does not change those basic recommendations. It reinforces why they remain necessary. During strong shaking, the most immediate danger inside many homes comes not from the ground itself, but from objects that fall, slide, or break. Securing shelves, televisions, water heaters, and heavy furniture can reduce injuries. Residents should also know safe locations inside their buildings and practice what to do rather than waiting to make decisions during the shaking. Preparedness is especially important in Southern California because the region combines significant seismic risk with a large population and complex infrastructure. Los Angeles, San Bernardino, Riverside, and the Coachella Valley are connected by highways, rail lines, water systems, power networks, and communication routes. A major earthquake could affect several of these systems at once. Modern building codes provide important protection, but no code can make every structure immune to damage. Buildings constructed under newer standards are generally better equipped to withstand strong shaking than structures built before modern seismic engineering. Even so, older homes, unreinforced masonry, vulnerable bridges, underground utilities, and aging infrastructure can remain serious weaknesses. A joint rupture across the San Andreas and San Jacinto systems could also produce different levels of shaking in different communities. Distance from the rupture, local soil conditions, building design, and the direction of rupture propagation would all influence the damage pattern. Some areas could experience intense shaking, while others farther away face secondary hazards such as fires, landslides, broken pipelines, or water system failures. The exact consequences cannot be known in advance. That uncertainty is one reason emergency planning uses scenarios rather than a single predicted outcome. Officials can prepare for a range of earthquake sizes and damage patterns, then adjust their response as information becomes available. The new research may help improve those scenarios by showing how a rupture could potentially move between neighboring fault systems. In the past, planners might have considered each fault separately. A model that includes interaction can reveal the possibility of longer rupture lengths, broader shaking, and more complicated transportation or infrastructure disruptions. The approach could also influence decisions about monitoring and public education. If Quezon Pass is a key junction between major fault systems, it may receive additional attention from researchers and emergency agencies. GPS instruments, seismic sensors, and geological surveys can help scientists observe how the region changes over time. But monitoring is not the same as prediction. Sensors may detect gradual deformation or small earthquakes, yet they cannot currently identify the precise moment when a large fault will rupture. Earthquake early warning systems can sometimes provide seconds of notice after an earthquake begins, but they do not predict earthquakes days, weeks, or years ahead. That distinction should remain clear. The study identifies an unusually stressed configuration, not an imminent earthquake. The phrase critically loaded describes the modeled state of the fault systems, not a countdown clock. Stress can remain stored for long periods, and a fault may release it in a smaller event, through gradual movement, or in a large rupture that cannot be precisely timed. The value of the research is therefore long-term. It improves scientists' understanding of how Southern California's faults may interact and gives planners a stronger basis for evaluating the consequences of different earthquake scenarios. It also demonstrates why neighboring fault systems should not always be treated as separate hazards. If the methodology continues to perform well, it could be used in other regions where faults run close together. Japan contains complex networks of active faults and earthquake zones. Turkey has several major systems capable of interacting during large events. Other densely populated regions around the world face similar challenges. The broader scientific shift is from asking, what can this individual fault do, to asking, how does this entire fault network behave? That is a more difficult question, but it is also closer to the way earthquakes actually unfold. Geological systems do not respect the boundaries of separate research categories. Stress moves through the crust, and a rupture may interact with nearby structures in ways that are not obvious from studying one fault at a time. For Southern California, this means that the Southern San Andreas and San Jacinto faults should be understood as separate systems with the potential to influence one another. Their individual histories still matter, but so does the relationship between them. Cajon Pass may be one of the locations where that relationship becomes especially important during a future earthquake. The present evidence does not establish that a combined rupture will occur. It shows that the modeled conditions are unusually favorable for interaction compared with the rest of the 1,000-year simulation. That is a serious finding, but it remains a probability statement rather than a prediction. The responsible response is neither panic nor dismissal. It is preparation based on the best available science. The newest research adds a carefully documented piece of evidence to the broader understanding of Southern California's earthquake risk. Two major fault systems, the Southern San Andreas and the San Jacinto, are modeled as carrying their highest combined stress levels in 1,000 years. They meet near Cajon Pass, a geographic junction that could influence whether a future rupture stays confined to one fault or crosses into the other. Scientists still cannot say exactly when that stress will be released. They cannot provide a specific year, month, or day for the next major earthquake. What they can say is that the present configuration stands out within the 1,000-year period represented by the model. The faults are highly stressed, and their similar stress levels may make interaction more plausible than it would be under a very different configuration. That does not mean Southern California is facing a guaranteed disaster. It means the region deserves continued monitoring, serious planning, and public preparedness. The research is not a prediction of imminent danger, but it is a reason to take long-term seismic risks seriously. The earthquake gate concept also offers a useful way to understand why fault interaction matters. A rupture on one fault may remain limited, or it may reach a junction where the neighboring fault is already under similar pressure. If the conditions are right, that connection could allow the rupture to continue across a longer section of the fault network. A longer rupture could mean stronger and more widespread shaking across communities, including Los Angeles, San Bernardino, Riverside, and the Coachella Valley. It could affect highways and rail corridors through Cajon Pass, disrupt power and communications, damage water infrastructure, and complicate emergency response across a large area. Modern California is better prepared than it was during the great earthquakes of the early 20th century. Building codes are stronger, engineering standards have improved, and emergency agencies have more information and better communication tools. But preparedness cannot eliminate all damage, especially during an event involving multiple fault systems. Residents can still reduce their personal risk through practical steps. Secure heavy objects. Keep emergency supplies available. Make a household communication plan. Learn how to shut off utilities if necessary, and understand the basic response during shaking. Drop, cover, and hold on. These actions are useful, regardless of the precise fault involved or the eventual size of the earthquake. The same principle applies to communities and businesses. Organizations can review continuity plans, protect essential equipment, identify alternate communication methods, and prepare for power or transportation disruptions. Local governments can strengthen bridges, water systems, hospitals, and emergency facilities. Preparation is most effective before an earthquake, when there is time to identify weaknesses rather than after the ground begins moving. The scientific work will continue. GPS monitoring will track deformation. Seismometers will record smaller earthquakes. Geological research will improve knowledge of past ruptures. As more data becomes available, researchers can update the computer models and test how closely their projections match real conditions. That process may not produce a perfect forecast, because earthquake prediction remains beyond current scientific capability, but it can produce better risk assessments. It can reveal which fault interactions deserve attention, which infrastructure corridors are most vulnerable, and which communities may need stronger preparedness measures. The key conclusion is therefore measured but important. Southern California's faults are not quiet because they are harmless. They are part of an active plate boundary where stress continues to accumulate. The southern San Andreas and San Jacinto systems have their own earthquake histories, but they also exist within the same connected geological environment. Their relationship may determine how a future rupture develops. The study does not say that a major earthquake is certain to strike soon. It shows that the conditions for a significant seismic event are more closely aligned now than at any other point in the modeled 1,000-year period. That finding should be treated as a warning about risk, not as a timetable for disaster. Beneath the roads, buildings, railways, and neighborhoods of Southern California, the faults continue moving slowly, storing and transferring energy over time. Most of that movement is invisible, but the new research provides a clearer view of how the system may behave when that energy is eventually released. If this explanation helped you understand what is happening beneath one of America's most populated regions, subscribe for more detailed breakdowns of major earthquake research. Share your thoughts about how prepared your own community is for a major earthquake. And remember that the most useful response to an uncertain hazard is not panic. It is informed preparation.